Well, thank you, Vlad, for that lovely introduction, and thanks to everyone here for coming to listen to some permafrost talk. So, first things first, we're going to be thinking today about permafrost and kind of thinking about whether it's actually so permanent, and kind of looking forward into the future and considering, whether permafrost is going to be around for much longer and what's going to happen as it disappears. So I'd like to start by acknowledging the Permafrost Lab. As Vlad mentioned, that's where we're housed in the Geophysical Institute. You can probably see a cultural theme here. It's Vladimir Romanovsky, Sasha Kolodov, Dmitry Nikolsky, Sergei Marchenko, and Colby Wright are the people that I share this lab group with, and they're great to work with. And then I chose this image here. This is a picture from the Beaufort coastline, a colleague of mine walking along and admiring this pretty dramatic coastline with big blocks of ice and eroding bluffs here. So the Arctic, as we're all quite aware now, and probably as you know, is at the front line of climate change. And this is in part because of something called polar amplification. So in this map here, you can see that in the higher latitudes, there is a darker red, and at lower latitudes, it's a lighter yellow, and this corresponds with greater projected changes in average surface temperature. And so by 2100, some of the most extreme projections suggest that we're going to see a change of up to 8 degrees Celsius in our surface temperatures up in high latitudes. And this is a big deal for us because we're edging towards a pretty critical threshold of 0 degrees Celsius. And for northern landscapes, this is very important because we depend on that threshold of 0 degrees Celsius for stability. Many of our communities in Alaska are underlain by permafrost, and some of this permafrost contains ice. And this ice is a wonderful foundation when it's frozen, but as temperatures increase, and especially if they increase by 8 degrees Celsius, this is going to lead to some significant hazards occurring in permafrost-affected landscapes. And we can see here, this is kind of a little schematic I put together, but I mean, this is a reality that we're kind of facing. So recently, Fairbanks ground temperatures have seen a renewed warming. I think if any of you have been to permafrost talks here in town before, you've seen Vlad's data that's kind of been logging ground temperature change since 1930. And so this diagram here, we can see along the x-axis, we have time, so 1930 through to the 2010s. And then these different lines represent different temperatures at different depths. And so we have our mean annual temperature for the ground at 0.08 meters all the way down to 1 meter. And you can see there's a general trend of warming at these different depths. And I've highlighted our critical threshold of 0 degrees Celsius, and we can see that many of these lines are beginning to cross or have already crossed this 0 degree Celsius threshold, which is really important to us. So the big question I want us to consider tonight really is, how will Arctic landscapes respond to ongoing and future warming? But first, I think it's pretty important to recap some important terms so that everybody's on the same page as we're going through this talk, and I'm throwing these terms around so that we all know what they mean. And I thought we should probably start with permafrost itself. And so this seems quite rudimentary, but it's important to think about. So permafrost is ground that remains at or below 0 degrees Celsius for 2 years or longer. And this map is a really beautiful map that shows the distribution of permafrost in the northern hemisphere. And we can see there's some darker blue colors. And this is where we have what's called continuous permafrost, where the permafrost is everywhere. So this is areas like the North Slope, where the whole landscape is underlain by permafrost. And then we have the lighter blues, which are gradually going through discontinuous, sporadic, isolated permafrost, so gradually getting a lower percentage of permafrost across the landscape. And so it's important to think about the fact that permafrost can be made of many different materials. It's basically any ground that is below 0 degrees Celsius for 2 years or longer. So this can include high mountain bedrock that contains no ice. It can be peat that's frozen. It can be a mixture of ice and silt. So in this picture here, we can see a huge ice wedge with some people for scale. And the different materials that permafrost is composed of really make a difference to how that permafrost is going to respond as we reach our critical ice cream threshold of 0 degrees Celsius. So that's our first term, permafrost. So our second term is active layer. And the active layer is the layer of ground which is subject to annual thawing and freezing in areas that are underlain by permafrost. And as we approach our 0 degree threshold and temperatures warm up, we expect this active layer to become deeper. And our third term is massive ground ice. And so massive ice, as I alluded to in these little schematics before, we have these large bodies of ice that exist below the ground surface. And these are potentially going to melt as we see increasing ground temperatures. So in this image here, we can see a person for scale walking on top of this very large ice wedge. So some of these ice bodies can be pretty huge, up to 30 meters in depth. And so if you think about this kind of size ice body melting, this could really cause quite a change to the surface topography. And here's a little baby ice wedge, just for comparison, which I thought looked pretty cute. But so we are expecting these massive ice features will potentially melt gradually or catastrophically as we get increasing temperatures. Which brings us to Thermokarst, which, if you've driven around Fairbanks at all on these roller coaster roads we have, you're probably all familiar with this. So Thermokarst is the hummocky terrain that forms when ground ice melts. And we expect that Thermokarst will become more prevalent with warming as we approach this 0 degree threshold. So some examples of Thermokarst landforms. Here we have a landscape up in the Canadian high Arctic, and there's some nice examples here of these polygonal patterns. So beneath these troughs, we have ice wedges, and when those ice wedges melt a little bit, we get these troughs that form. We have Thermokarst lakes that form. If these troughs, the ponds and the troughs become larger and coalesce and join together. We have these gullies that are formed from Thermokarst and thermo-erosion. And we have these little baby ponds that form too. So this is a pretty important term, and especially looking forward as things start to warm up, Thermokarst is going to become a really prevalent process for us here in Alaska. And so the final term that's maybe a newer term that hasn't come up so much so far is Talik. So this is where we have a layer of unfrozen ground within a region of permafrost. And to date, most research or most talks have kind of talked about taliks in the context of these Thermokarst lakes. But we're now seeing that taliks forming in areas that aren't associated with lakes, which is quite a big new process that we're beginning to observe. So going back to our question, how will Arctic landscapes respond to ongoing and future warming? Let's think just a minute about why we actually care about this question. So we touched on this briefly, of course, infrastructure and damage to infrastructure. Here is an image of, this is a LiDAR survey of the Goldstream Road area, and you can see this kind of dimpled terrain, these ice wedges where the tops of the ice wedges have melted, and we have this roller coaster. Has anyone here driven on Goldstream Road? Yes. And you're shocked, you're like, oh my God, how often am I getting replaced? It's like, So these roads at Goldstream, many other roads in town, it's like a free roller coaster ride. It also comes with expensive shock replacement and long waits in construction. So in Fairbanks, we're very familiar with this impact. It's expensive for us because we have to repair our cars, expensive for DOT because they have to fix the roads. So on a broader scale, if we think about this statewide, especially kind of the whole road moving northwards, permafrost degradation is very expensive. And then if we zoom out even further and we think about the whole Arctic, there was a recent study that suggested 30% of Pan-Arctic infrastructure is at risk from ground instability, Thermokarst, by 2050. This is a lot, and this is going to impact a lot of northern communities that we're familiar with. So this is an aerial shot of Ukqiavik, formerly known as Barrow. So communities such as Ukqiavik and other northern communities, Kaktovik and Point Ley, and then obviously in Russia as well, a lot of communities, and then a lot of industry too. We have a lot of oil industries development up in high latitudes, and this is going to become incredibly expensive as we see permafrost degradation progressing. So this is one of the reasons we care about what's going to happen to permafrost. And the other reason is probably more sensational, so changes to the carbon cycle. So permafrost is a wonderful freezer, and it's locked up a lot of organic material over thousands of years, and it is kind of it's estimated to contain about 1,700 petagrams of carbon, so that's about double that in the atmosphere. But this is locked up, some of this stuff is at tens of meters depth, so it's like very variable as to when this stuff's going to be released. But this high carbon content has led to these very sensationalist headlines, this methane time bomb, the Arctic carbon bomb. But really, we actually don't know if this is going to happen or when this is going to happen, because the system is horribly complicated. And we really don't know how warming is going to impact the Arctic and whether it's going to result in more drawdown of carbon or more release of carbon. So I think the carbon time bomb is a little sensationalist, but we definitely need to think about how permafrost degradation is going to impact carbon cycling. Okay, so for real this time. How will Arctic landscapes respond to ongoing and future warming? So I thought about how best to approach this, and I decided really we need to kind of look at this in three different ways. I think we need to look at the past and the legacy of the past on our landscape around Fairbanks, because it's a product of tens of thousands of years of geologic processes. And then we need to think about the present and what we're observing right now. And we can kind of combine these things and then look to the future and have a better idea of our trajectory and how things might change. So let's start in chronological order. Had to get an iconic mammoth picture in here somewhere. So we're going to think about past legacy effects and what Alaska used to be like before today. And so I kind of want to step back really far, and I'm going to have a lot of these diagrams with time along the x-axis, and they're going to vary drastically. So this one's millions of years, and they're going to vary from millions of years to years. And so here we can see time before present, from 0 back to 60 million years. And I just wanted to add this in because it's kind of neat to just think about, like, when did it get cool enough to get permafrost in the first place? And so we can see here, this is the Cenozoic period, and we have generally, through time on the x-axis, on the y-axis, we have temperature, and so warmer at the top, colder at the bottom, and you can see that over this 60 million year period, we have this gradual cooling. And it's pretty amazing to think about that, around 40 million years ago, we had Antarctica started to form. And then around 11 million years ago, we had the Northern Hemisphere ice sheet. So this would be Greenland and the Laurentide ice sheet, so the ice sheet that existed during the last glacial maximum. And then we have the arrival of permafrost. So permafrost began to develop on the landscape around 3 million years ago. So it's a relative newcomer, really, in the cryosphere, but we won't harp on about that. So zooming in time, so the x-axis has now changed to thousands of years before present, we can think about how during glacial and interglacial cycles, permafrost kind of waxes and wanes. So we have really extensive permafrost, like all the way down to Ohio during the last glacial maximum, during the glacial cycles, when it's really cold. And then we have permafrost degrades, and the extent of permafrost really shrinks back during the interglacial periods. So these are warm periods, like the one that we're in right now. And so if we think about this, and we think about the life of permafrost, the stuff that we are driving over when we drive along Goldstream Road, on the roller coaster, this stuff, some of it formed tens of thousands of years ago. So this stuff would have formed during the last glacial cycle. So this is 110,000 years to 12,000 years before present. And so some of this permafrost is really, really ancient, and it's been sitting in the ground for a long time. And so to think about the fact that this stuff is degrading is quite incredible. So let's take a look at Alaska during the last glacial maximum and kind of think about what would this environment have been like. So surprisingly, given how far north we are and how cold it is, Alaska was actually not really glaciated extensively. Where we are right now, it wasn't glaciated at all, and up on the north slope wasn't glaciated either. So in this map, you can see the white is the Laurentide, the dark blue is continuous permafrost, and the light blue is discontinuous, but this would have all been continuous during the last glacial maximum. And this place would have been really inhospitable. We had this giant ice sheet across most of Canada and then down in south central Alaska, which would have made for just horribly windy, dusty conditions. Like, it would have been a really miserable place to be. And then we also had really frequent marine transgressions, which is where the coast comes on shore further, and we get the landscape flooded by the coastline. And so the point here is that the whole landscape would have been subject to all these different depositional environments, and this has a really big impact on how permafrost is today. So something that really surprised me when I came to Alaska and started doing geology here was 15% of Alaska was affected by sand deposition during the last ice age. And even now today, we have these amazing areas of sand dunes in Alaska. So this is the Noga-Habara sand dunes in western Alaska. But what's interesting about these areas, it's pretty extensive, 15%, is that they really don't contain much of this massive ground ice. So the stuff that causes this thermokarst is absent. So really these areas are going to be fairly stable from a geomorphological perspective, so the landscape is going to be fairly stable if it warms up. But on the edge of these sand seas, the finer material settles out, and we get these areas of ice-rich silt that contain huge bodies of ice. And unfortunately for us, we are in one of those areas. So we have massive ice wedges like this in the Brooks Range foothills, but we also have them in Fox and in many areas around Fairbanks. So there are some really, really huge ice wedges that have formed in what we call loess around here. If they melt, it's going to cause some pretty catastrophic changes to our landscape. So areas that have this ice-rich loess have very high thermokarst potential and a high potential for hazards, basically, if we have rows of buildings in these areas going into the future. So the result of all these different depositional environments, the sand, the marine transgressions, and the silt, is that Alaska is a really complicated mosaic of different ground ice contents. So these pictures of the big ice bodies I showed, they vary hugely depending on where you are in Alaska. And so each color on this map, the red is where we have a lot of ice, and the orange is where we have medium amounts of ice, and the yellow to white is where we have low. So that's where we want to be, but unfortunately, we're in this messy area that has a lot of ground ice. So that's kind of the idea behind this legacy effect, is thinking about these different depositional environments and how they kind of prime the landscape for either being more stable under warming or more vulnerable to thermokarst development. So that brings us to present-day observations that we can kind of lay over this understanding of the kind of foundation of permafrost in Alaska. So let's have a look at what we're seeing today. So with the Permafrost Lab, we have a really extensive network of monitoring stations. And these are really incredible records because some of them go back tens of years, and they provide us with really great baseline data to see just how temperatures are changing through time. And so we have a lot of permafrost boreholes that are located along the Haul Road, and quite a lot over on the Seward Peninsula. But we also have boreholes over in Russia and in the Canadian High Arctic as well. And so having this really diverse array of boreholes enables us to see how permafrost temperatures are changing across the Arctic, and we can join up with other projects and look at their boreholes and see, okay, so what does the whole northern hemisphere look like when it comes to ground temperature? And you probably won't be surprised when I tell you that we're just seeing, in general, warming across the whole of the permafrost region. So this graph is only years along the x-axis, just single years. So time along the x-axis here, and then ground temperature along the y. So we have our critical 0-degree ice cream threshold, and then we go all the way down to -15. And so there are not many boreholes in this colder section of the graph, and there are a lot of boreholes in this section up top that are creeping very close to this 0 degrees Celsius threshold. So what impacts are these warming trends having on our landscape? I'm going to talk about three main areas of observations that we're making, or three key observations that we're making. And the first is one that surprised us, and that is that we're seeing incomplete refreezing across subarctic Alaska during the wintertime at new sites. At sites where we used to see complete freeze, we're now seeing incomplete freeze during the winter, which is shocking in some ways. So in this map, we can see a bunch of dots in Alaska. So these different colors correspond to our different types of permafrost. We have our continuous in the north and the discontinuous in interior Alaska. And so each dot represents a monitoring site, and the green is where we have we don't have any incomplete refreeze. These sites that are green are refreezing in the wintertime. At the red sites, we already had no permafrost. But the yellow sites are where we see this new trend happening. And so these yellow sites, you can see there's some around Fairbanks, there's some on the Alcan, and there's some on the Seward Peninsula near Nome. And at all of these sites, in recent years, we've seen incomplete refreezing of the permafrost, which is a big deal. And so we're going to take a closer look at Bonanza Creek, which the arrow is not quite accurate, but it's just outside of Fairbanks on the Parks Highway. And we're going to take a look at ground temperatures and see what's going on. And so this diagram shows us from 2010 through to 2019, the ground temperature for 3 different depths at Bonanza Creek. So we have our thermometers in the ground, and I've pulled out these 3 different depths. So we've got 22 centimeters below the surface, half a meter in blue, and then 1 meter in green. And so you'll see that the pink one really, it changes significantly. And you can see that the amplitude is pretty high. It gets warm, it goes cold because it's very near to the surface. And as we go deeper, we can see that this variability decreases. But one thing that is for sure is that we can see that through time, the cold temperatures are definitely not as cold as they used to be. So we started off seeing temperatures as cold as only -10, and now we're not reaching anywhere near that depth. So if we strip away all the depths apart from 1 meter depth, we basically see that this permafrost is dying, and we can see that it's essentially flatlining now, where we are no longer seeing freezing at 1 meter depth, where it used to go down to -5 degrees Celsius. The ground is now hovering around 0 degrees Celsius throughout the winter. And so you can see these 2 arrows basically point to the winters of 2017, 2018. There might be an arrow that points to 2019, but we'll see how this next cold snap goes, or this forever long cold snap that we're in. So this is kind of the story at a lot of these sites with the yellow dots, as we basically see these temperatures getting warmer and warmer, and we see these deeper thermometers are showing us that we're not getting freeze any longer. So if we think about this in a schematic form, this is what we should be getting. In the summertime, we have thaw, and we have intact massive ice wedges, and in the winter, everything freezes up, and the permafrost is really healthy, and it's good. But what we're now seeing is that we have thaw in the summertime, and it's a little deeper than usual, and then in the wintertime, we're having freeze, and it's a little shallower than usual. And these 2 things combined mean that we have this talik, this thawed layer that forms within the permafrost. And the really unfortunate thing is that this gives the next summer a big jump start on how much thaw we get. So we're getting deeper thaw layers as a result of these taliks. And so just briefly thinking about why this is happening is primarily because we're having warmer winters and warmer summers. So both of these things combined. So what we used to have was that winter freeze was much greater than summer thaw, and we had permafrost and then our active layer. But now we're moving into this phase where winter freeze is much less than summer thaw, and we're now developing this seasonally frozen layer. We don't even have an active layer, and we're having this ice cream talik layer forming, and it gets thicker through time. And so we looked at our ground temperature data, and we looked at some historic climate data, and we looked at some future projections. And this graph is quite a lot, but I'll walk through it really quickly. But so we have year along the bottom here, and then we have depth of thaw or freeze. And basically what we see is this orange line is summer thaw, and it's getting gradually deeper. And we have winter freeze in blue, and that's gradually getting shallower. And where those two lines cross is where we get a talik forming. And we can see that right now, this is 2020 here, and we can see that we're about to cross this threshold where we're going from this being kind of an intermittent event to one that happens, that happens every year. So this is a pretty significant change in the permafrost around Fairbanks and interior Alaska. So I want to go on to the second observation that we've made, and that's moving up to the Canadian high Arctic. So this is the Canadian archipelago, and in this region we've seen really rapid Thermokarst development, so ground subsidence due to these massive ice bodies melting. So looking at this on a map, you can see we have these 3 islands and our 3 study sites across the Canadian archipelago. And these sites are characterized by very cold permafrost. So around Fairbanks, our permafrost is kind of close to 0 degrees Celsius at 1 meter's depth. But if we go up to the Canadian archipelago, we can see that the ground temperature here is up to like minus 14 degrees Celsius, which is very cold, and we would think that this would be quite stable permafrost. It would be fairly safe from the impacts of climate change until later on, until things are more advanced. But if we take a closer look at Mole Bay, we'll see that this isn't the case. So it's a beautiful tundra landscape. Well, to me, this is beautiful, beautiful tundra landscape. And it's characterized by 2 important attributes. And that is that because it's so cold, the landscape was in equilibrium with the climate until very recently. And we have these big bodies of ice that were basically forming until a couple of decades ago. And so the ice is incredibly close to the surface. And the other thing is that this permafrost, or the ground, is fairly naked. It doesn't have much vegetation. So here around Fairbanks, we have this really thick moss in the black spruce forest, and it acts as a really nice buffer against warming. Whereas in these areas, if we have a run of hot days in the summertime, that immediately impacts the ground because that heat can flow straight into the ground because there's no vegetation protecting it. And so here you can see there's some ground ice close to the surface. And this ground ice basically melted really rapidly over a period of just over 10 years. So here you can see the terrain in 2004 is very flat, none of these ponds or pits. And then we went back in 2016 and we found that there were just loads of these ponds that had formed, and there was up to 90 centimeters of subsidence, so kind of like your kitchen countertop, which is quite a lot. And so this whole landscape had completely transformed in what is really a short amount of time considering how long this landscape has been stable for. And so we were like, wow, this is a huge change. And like, why did this happen? So we went and looked at the climate data, and unsurprisingly, we found that warmer summers had really caused this landscape to transform quite rapidly. And so you can see here a lot of wiggly lines, but in essence, these dotted lines are what we think of as normal temperatures, and the colors correspond between the dotted and the blobs. And we can see that all the dotted lines are where summer warmth is low. So our blue and green lines down here and our orange line. And then all the observations, so these blob lines, are above the dotted lines, so above the historically normal climate. And so this series of warm summers basically caused this landscape to completely transform, which is wild, because this landscape has been stable for hundreds and thousands of years. So Captain Cook reaches Alaska, this landscape's just hanging out. The Roman Empire is going on, this landscape's just hanging out. We have our first agriculture. This landscape's been here for a really long time, possibly much longer than this. And now we're seeing this transition from a very stable landscape such as this to one that has tons of ponds and huge amount of topography for this kind of landscape. So this was another really surprising observation that we'd made in combination with this Talik formation in interior Alaska. And so the third type of observation is more kind of less based on monitoring and more based on surface observations. And it's on hill slope failure events, so landslides essentially, and mass movement events. So has anybody heard much about the Denali Park Road landslide? You guys hear about this on the radio? And yeah, so it's become a pretty big deal, and the Park Service, this was back in December, this article, but the Park Service were debating whether they would have to close the Park Road next summer because of the Pretty Rocks landslide moving so rapidly, and they're really having to put a ton of money and materials into keeping up with road maintenance and making sure this section of the road is stable. Has anyone here driven or gone on the bus past this section? Yeah, it's pretty hair-raising, huh? It's a pretty scary section of road, so the fact that it's like slipping away down the hillside is quite unnerving. But so I'm going to talk about hill slope and mass movement events in different areas across the Arctic, but we'll start with Denali Park. So we're here at Ravens Landing, which is 64 degrees north, and Denali is about the same, right? It's a 2-hour drive south. So we've been working together. Zena, who's here. Hi, Zena. I'm going to put you on the spot. So Zena Robert, she's a master's degree student here at UAF in the Geoscience Department, and she's been looking into whether permafrost degradation is causing an increase in mass movements along the Park Road in Denali. And she spent the last summer out hiking around and doing surveys on these different landslides. There's tons of landslides along the Park Road. And she was looking for evidence as to whether permafrost degradation could be, causing these landslides and these mass movement events. And so here's one example that she found. This is the mile 35 slump. I should have outlined this, but here's the head of the landslide. This is a photo that Zena took last summer, and the toe of the landslide. And hiking around on this landslide, Zena, this is a little difficult to see, but found evidence of ice on the headscarp of this landslide, suggesting that maybe ice melt had caused this failure to happen. And there's many slides along the road where we think this is the case, but we don't quite understand what the temperature regime is. So we're working with Denny Capps, who's the park geologist, and this summer, Zena and I and Vlad and some others are going to be looking at putting some monitoring sites along the Park Road. So here are the yellow dots. We're hoping to monitor permafrost. And so we're looking at this area where the red is where there's no permafrost. This is a map that Santosh Panda, who also set up this awesome little display for hot times and cold places, he modeled where there was permafrost in Denali. And so we're kind of looking at these areas on the cusp of whether there's permafrost or no permafrost and trying to work out how the ground temperature is changing and whether this is going to cause more landslides to happen. So this is close to home. So moving further north, there's been a lot of observations of increased mass movement events also on Banks Island, which is where we have observed this rapid thermokarst too. And so this is work by Canadians Tony Lewkowicz and Robert Way, where they found this pretty astounding transition in the landscape. So on the left-hand side, you can see these little thaw slumps. They were really not very prevalent in 1984, and then by 2013, we just have a huge increase in the number of these red dots. And they attribute this to these warm summers. Just these single warm summers can really trigger a really huge response across the landscape. And then just moving north quite a bit further, I think this is the winner for the coldest permafrost. So this is Melissa Ward-Jones's work, and she found the same pattern where even up in Eureka, so this is 80 degrees north, which is incredibly high latitude, where she's also observing this increase in summer air temperature is causing these really widespread changes across the landscape. I think Melissa's here too. Yes. So Melissa's just arrived here as a researcher at UAF, and it's going to be great having her on board. But she observed these big thaw slumps across the landscape and found that these correlated with these really warm summers. So we're seeing this across the board. These very sensitive but very ancient landscapes that have been stable for a very long time are responding to these anomalously warm events. And it's being observed by many different lab groups. So that's kind of the wrap I have for these observations that we've made and the big findings that we're really kind of surprised by recently. And so that takes us to looking at future projections. So how do we know when this is going to happen and where it's going to happen, right? So we kind of have a slightly better idea now. We have this idea of these paleo legacy effects, so where we have our ground ice or where do we have our sand dunes, that means there's no ground ice. We have our observations. Here's Vlad trying not to get tangled up in a monitoring site up in Barrow. So we have our observations, our ground temperatures, and then we can also combine this with modeling and climate projections. And when we combine these things together, we can have a fairly good idea of where we're going to see dramatic changes taking place. So Dmitry Nikolsky, who's in our lab, has worked with Sergei Marchenko and Vlad Romanovsky to create this interactive map. If you're interested in permafrost, I'd encourage you to note down this website and take a look. You can slide the time scale back and forth and look at how permafrost is going to change for this area. We're working on the Fairbanks area. But you can see, so this map here shows our present day ground temperatures. And as you would guess, blue is good. It's cold. We like blue. And so up on the north slope, we have these ground temperatures around -6, -2. Good. We're not near the ice cream zone yet. But if we zoom forward to 2100, we see a lot of bad red. So we're seeing our temperatures increase in the Brooks range here to above freezing, and on the north slope to very close to freezing. And then down on the Seward Peninsula, we also see above freezing temperatures by 2100. That's a big deal. This is a large area of permafrost. So what about Talik distribution? Well, Dmitry modeled this as well. And we found that by 2090 to 2100, again, with this, it's actually all bad. Wherever we have color, from blue all the way through to red, but red's really thick. So we actually have Talik formation all the way up onto the north slope. And so the problem with this Talik formation is, that we get these kind of sped up rates of permafrost degradation. So by 2100, and probably much sooner, we're going to see some big transformations with permafrost. And as I said, we're currently working on the Fairbanks map. Give us another year, and I think we'll be close to that. And so thinking about kind of like the general picture here, so to predict how Arctic landscapes will change, we need to combine our understanding of geologic legacies, so these Pleistocene legacy effects, with our observations, so our really epic boreholes and our field observations, like Zena's observations in Denali, and then we can combine these and have a better understanding of how the landscape's going to change. And so our recent observations show that many areas in interior Alaska and the southern Seward Peninsula are no longer completely freezing during the winter, and that this is because of warmer summers and warmer winters. And then up in the high Arctic, we have these really cold, what were supposedly very stable landscapes that are now responding very rapidly to warmer than normal summers through Thermokarst development. And then across the Arctic, at all those different latitudes, we're seeing these hill slopes begin to fail, and we're seeing more of these mass movement events taking place. And in many cases, we think that permafrost thaw is to blame, and up in the Canadian high Arctic, we know that permafrost thaw is to blame. And these future trajectories show, in general, as we can see from Dimitri's cool model with the sliding timescale, that this thaw will continue, and these processes are going to become more widespread and more pronounced through time. So I wish I could end on a lighter note, but at least we're informed. And with that, I'd like to say thanks very much for listening, and I'll take any questions you have.